Hello everyone, I'm Yuhan. This talk is going to be about generalized deep 3D shape prior via part-discretized diffusion process. Our work aims at designing a unified 3D shape generative prior model, which serves as a generalized backbone for multiple downstream tasks. On one hand, to precisely capture local-fying detailed shape information and address the cubic increase in computational complexity, a vector-quantized variational autoencoder is utilized to index local geometry from a compactly learned codebook based on a broad set of task training data. On the other hand, a discrete diffusion generator is introduced to model the inherent structural dependencies among different tokens. In the meantime, a multi-frequency fusion module is developed to suppress high-frequency shape feature fluctuations, guided by multi-frequency contextual information. Chapter 1: Research Background. The motivation of our work is that the graphics community has developed a number of task-specific pre-trained models, tailored for unary tasks such as 3D shape generation, points cloud completion, and conditional shape prediction. Since above individual 3D generative representations do not share common knowledge among tasks, to migrate a trained 3D shape network from one task to another requires troublesome end-to-end model rework, and training resources are also wasted. For instance, a good shape encoding of chairs based on a general prior 3D model could benefit shape completion of a given partial chair and text-guided novel chair generation. Note that recent models such as AutoSDF and Lion explore multiple conditional generative frameworks. However, AutoSDF is defective in diversity and shows mode collapse in unconditional and text-guided generation, while training and inference of Lion are costly. With the belief that a good 3D prior model should support high-fidelity, diverse, and cross-modal shape generation, we have designed a unified model framework to learn shape priors for various tasks. It can not only be trained on different tasks with the same framework, but be transferred to extended applications with little or no fine-tuning as well. During the model design process, we primarily encountered three challenges: 1. High-dimensional nature of three-dimensional data and the cubic increase in computational costs with resolution. 2. How to effectively represent different modalities of data input across various tasks in a unified manner. 3. How to alleviate the presence of noise in the generated surfaces of shapes. Chapter 2: Methods. The two-stage training architecture is visualized here. The first stage is discrete part-based geometry encoding. While most encoder-based methods choose to embed shapes into continuous space via VAE, we propose to simplify the search feature space by introducing patch-level VQVAE to learn a compact and efficient representation. As it's flexible to encode interdependencies between parts, this encoding scheme provides a compact way for expressing highly diverse structural variations with high-quality local parts. The input of VQVAE is TSDF grids of 64 cubed, and the final representation is their component tokens indices in codebook. Given the above pre-trained VQVAE encoding and corresponding indexes, the popular solution is learning the joint distribution with autoregressive models. However, this scheme has several drawbacks. 1. Error accumulation. Geometry tokens are predicted one by one, therefore errors induced in the earlier sampling time steps will never be corrected in the subsequent generation steps. 2. Unoptimal generation order. Most autoregressive models perform a unidirectional prediction process, which obviously ignores the underlying complex 3D structure. And 3. Lack of diversity. Without sufficient randomness injection, deterministic transformer backbones easily lean towards mode collapse. In view of these limitations, we develop a discrete diffusion generator to iteratively sample in the time domain with all local part codes updated simultaneously at each time step. Instead of using the commonly employed Gaussian diffusing, we adopted a categorical diffusing approach, which is specifically designed for discrete input representations. In discrete forward process, we use transition matrices Q characterized by uniform transition probabilities to describe the corruption. As a result, all local part codes can be transformed to any other shape codes with the same transition probability, producing complex 3D structure representations. Mask token is also introduced to assist the network to locate where is need to pay attention to more easily. In the backward process, the training objective consists of the MSE of recovered original shapes from ground truth and the distance of the posterior. Moreover, local atomic indexing potentially offers unified and well-aligned local representation among different modalities, which greatly facilitates cross-domain conditional shape generation. But we still observe noisy surfaces with outliers from generated shapes, mainly introduced by categorical corruption. Namely, our categorical corruption has equal probability to transit a token into any completely irrelevant shape tokens, and it is hard to recover the correct category of this shape token. To remedy this issue, inspired by the observation that corrupted tokens' neighbors still possibly remain unchanged and provide dependencies, we develop a multi-frequency fusion module. It looks into local contextual regions and extracts low-frequency components by downsampling to suppress high-frequency outliers. The ablation study has demonstrated that MFM effectively smooths out the generated shapes, filtering out some high-frequency components that may arise from surface roughness and outliers. Chapter 3: Experiments. Next, we demonstrate the experiment results in unconditional shape generation, shape completion, and text-driven generation. Our 3D-QD prior is capable of helping synthesize high-fidelity, diverse shapes with smooth surfaces, outperforming multiple state-of-the-art methods. In addition to the above major tasks, we show that 3D-QD can be extended for a wide range of downstream applications, serving as a generalized prior. With no tuning or retraining, our model successfully recovers noisy inputs into clean samples, demonstrating the noise immunity ability of our pre-trained 3D-QD. It comes from the noise compatibility from diffusing training and quantized noise-free vectors in codebook. We conduct an experiment on text-guided shape editing without any tuning and single-view 3D reconstruction with a little fine-tuning on Pixel 3D dataset. To statistically analyze the novelty of the generated shapes, we visualize the distribution of light field distance between our generated shapes and retrieved shapes. Note that our 3D-QD can generate novel shapes that are different from the training data. We further visualize our learned prior distribution to provide an in-depth analysis of how the underlying shape structure distributions for various object types are well modeled by 3D-QD. As for the efficiency, we compare our model with the latest 3D diffusion work line about training and inference complexity, evaluated on single-class shape generation tasks, proving the efficiency of our discrete framework. That's all I want to introduce about our 3D-QD. Thanks for your attention.